Michael, good morning.
Hi, good morning, sir. Can you hear me?
I can hear you, yes. Can you hear me?
Awesome, perfectly. How are you?
Good.
Perfect, perfect.
What's up?
Yeah. Um, Going pretty well actually. I do have a few questions about Mathematica though, and I was hoping you could help me get through them.
Yeah, we'll take a look. Let me load up Mathematica here while we're talking. Okay, what's going on?
Perfect. I actually just want to start off with a question. Let me screen share here. I was going through the videos, and when it came to this question about checking the concativity,
Yeah,
I
concavity.
wanted to ask, right, if this was coded correctly, just out of curiosity, if it's intentionally XX or whether there should be a Y element here.
No, this is the above scroll. Yeah. So for analyzing these local maxima and minima,
Hmm.
first thing to do is to find the derivative, set it equal to 0, and solve. This
Hmm.
this will give you the critical points. And now, if you want to find out if the function is concave up or concave down at those critical points. And
Hmm.
in if you're doing this in one dimension, the first part is exactly the same. Take the derivative, set it equal to 0, and solve. And in one dimension, then you take the second derivative, and if the second derivative is positive there, then it's concave up. And if the second derivative is negative there, then it's concave down. And if the
Hmm.
second derivative is 0, then this test doesn't tell you. But this is the second derivative test for one variable right here. But in multivariables, it changes. The first part is sort of the same. You do that. But now the second part has number 2, it itself has 2 parts. So you find the second derivative. So this is part 2a. You find the second derivative, which is a 2 by 2 matrix. And that 2 by
Right.
2 matrix is fxx, fxy,
Y.
fyx, fyy. And then you find the determinant of the second derivative. And this is called the Hessian. So the Hessian formula is fxx fyy minus fxy fyx. And these two are the same for the functions we're dealing with. So this boils down to fxx fyy minus fxy or fyx squared. So this is a formula for the Hessian. This is the first thing that you compute. And now I'm going to erase this because there's more, even to part 2a.
Right.
So you find this Hessian. And if this is bigger than 0, then the point you have, the critical point, is either a max or a min.
Hmm.
But it doesn't tell, this being positive does not tell you which it is. It only tells you that it is. And if the Hessian is less than 0, then the critical value is a saddle point. Saddle point means that it's concave up in some directions and concave down in other directions, like a saddle on a horse.
Would it be correct to say that a saddle point is a 3D inflection point?
It is one of several kinds of 3D inflection points, yes.
Okay.
So that would be correct, but there are other kinds other than this kind of saddle point. So that is part 2A. This is the first part of the second derivative test. And then the second part, which I'll put up above. Can you still see this, Michael, up here?
I can actually. Yep.
Yep. Then the second part says that under the conditions 2A1, so under the condition that you do have a max or a min, then it's the same. Fxx, the second derivative, positive implies minimum. This is a point at which a minimum occurs, and Fxx less than 0 implies this is a maximum. Or you could do, as an alternative, you could do Fyy. It says if either of the pure second partials are positive, then it's a minimum, or if either of the pure second partials is negative, then it's a maximum. But these do not tell you max and min unless the Hessian is positive.
Okay, now I understand it. Okay. I thought there was a coding error there. Now I get why it's that way.
Yeah, so now if you go back to your question was about why is that XX? And that's because now we're checking a pure second derivative, and one that only uses x's. So we are in this case up here.
Mm-hmm.
So you only need that information providing AB is a critical point and that the Hessian at AB is positive.
Right. Okay. That clears it up for me. The other question I had to do. Here it is. It had to do with the second part of testing the boundaries of maximum and minimum themselves.
Yep.
Or maximum. I can find. Right. I can find simply using, for example, maximizer and maximizer minimize easily. But what I'm struggling to do is coding this second part. So, for example, on a triangle,
let me
you find,
if you would blow that up a little bit so I could see it.
Right. Let me do all of those.
You can do that whole section. So this is classifying, here we're classifying the critical values inside.
Mm-hmm.
So, and then that's using the second, yeah, okay. So now restricted to the boundary.
So from what I gathered from the videos, the next step would be to segment them into lines, at least for the triangle.
Yep.
Which I can do, and I coded here. But then I'm not sure how to code, how to test them or how to set them equal to 0, which would be the next part.
Yep. So backing up just a little bit, in general, there are two ways to handle many of the problems that we deal with, but min-max problems, max-min problems are that way. One is to find exact values. One is to find approximate values.
Mhm.
And when you're using when you use Mathematica, then and use which maximizing and minimizing function were you using? Maximize?
I prefer n maximize.
Yeah. So when you use n maximize or n minimize, these are approximate. But you can also use Mathematica or by hand to do exact computations. And what we are talking about right here is this side right here. So you have a triangle, and you have some function involved, f of x and y. I'm just going to create one here, x squared minus y cubed x plus 4, something like this. And we have a triangle, and let's say we know that a couple of points, maybe 1, 2, and 4, 3. These are two of the vertices. Then the boundary, this is a triangle T, the boundary of T has 3 pieces, line 1, line 2, and line 3, or segment 1. So the boundary of T consists of those 3 segments. And because it's got corners here, you are obliged to do these one at a time. So we're going to find the maximum, minimum here, here, and here. It's very similar to the one-dimensional case where you have to check the endpoints, and those are checked separately on an interval, A and B. And we're going to be using that in just a second. So let's actually do it for the problem that I just put up here. So we have 3 jobs to do. The first one, say, is L1. So now we have to describe L1 mathematically, which means find a parameterization for it, a parametric function that describes it. This is easy, so I'll call it, I don't know, U1 of T. It's one-dimensional, so only one variable. 1, 2 plus T times the vector that goes between them, which is 3, 1. 0 less than or equal to T less than or equal to 1. When we did parameterizations of lines early in the course, lines between 2 points, it always works the same. Lines at this point should be pretty straightforward how to do it. And the fact that T can go between 0 and 1, there are other ways to parameterize this, but any parameterization will work. Any mathematical description of this line will work. And now you don't want just U1. This is only the first step. Then you want to find the function value on U1. And on the practice exam and on the other exams that we did, exam 2, I actually asked you to graph this so that you knew what you were looking at, but we can figure it out right here. If I
So could you tilt the screen down a little bit more?
Yep.
Perfect. Perfect.
If I work this out, the x value will be 1 plus 3t, and the y value will be 2 plus t, 0 less than or equal to t less than or equal to 1. And so f of u1 of t, f is x squared minus y cubed x. So this is x squared, so that'll be 1 plus 3t squared minus, and then y cubed, 2 plus t cubed times x plus 4. And again, 0 less than or equal to t less than or equal to 1. Now, working this out, if I simplify this, I can actually do this by hand. But now you have a function of just t, and you know the domain. So you can plot this. T is between 0 and 1. F composed with u1 of t. We have a formula for it. This is the formula. It's a little complicated, but not bad. 1 plus 3t squared minus 2 plus t cubed times 1 plus 3t plus 4. So there is the formula. Now you want to find the maxes and mins for this. So you go into the max min mode. How do you do it? First step is to find the derivative, set it equal to 0 and solve. And our variable here is not x, it's t. This will find you the critical points. And then you can find the second derivative at the critical points. If it's positive, it's a min. If it's negative, it's a max. And that will give you the t values at which you have maxes and mins. You also have to check 0 and 1. F of 0 equals, F of 1 equals. So once we do all this, then we will have the maximum minimum of the function on 0 and 1.
Okay, I think I get that now.
Okay, now the point at which this occurs, let's suppose that when we do this, we could actually use Mathematica to do this right now. I can maybe do that. So I'll just, where am I here? There we go. So F1 of t, FU1 bracket, t colon equals, and this would be 1 plus 3t squared minus y cubed, that's 1 plus 2t cubed, star for times 2 plus t squared. Times 1 plus 3t plus 4. Let's make sure it knows it. Looks like it did. Let's just plot this. It'll give us an idea where the maxes and mins are. T between 0 and 1. Of course, it didn't do it. All right. So, Michael, let me share my screen here. Get a huge number of things open here. There we go. So here is the picture of the graph. So I just plotted this function. And the function plots quite negatively. It just goes down. So the picture will tell you what to expect from this work. That the minimum will occur at 1 and the maximum occurs at 0. This is the function f of u of t, or u1 I called it. And so t equals 0 will give you the maximum point. And we need to find what point that is actually. So t equals 0 will yield the max. I will unshare now. So t equals 0 yields the max, and u1 of 0 will be the point in the plane where the max occurs, which would be 1, 2. So this is the point at which the maximum occurs. And the actual maximum will be equal to f of 1, 2. We could have read that off of the graph. It is this height right here, but we can plug into the function. X squared is 1, y cubed is 8, so that would be 1 minus 8 is minus 7, plus 4 is minus 3, so the maximum is minus 3. That's the minimum, sorry about that. That's the minimum. No, that is the maximum. T equals 0 is where the max happens to be negative. So the maximum of the values is f of 1, 2, which is minus 3. And then you do the same thing to find the minimum value, which occurs at 1. T equals 1 will yield the minimum value. Where does it occur? Well, it occurs when you plug in 1 for t in this case, which gives you the point 4, 3. And then the minimum value equals what you get when you plug in 4, 3 into the function. 16. The next one's going to be big. 3 cubed is 27. 27 times 4 is 108. 16 and 4 is 20. 20 minus 108 is what? Minus 88. So the minimum value is minus 8. Get it by plugging in that xy value into the function. So this is a simple case where the max and min occurred at the endpoints, but they needn't. I mean, the function could look like this. So the max could occur somewhere in between, maybe a fifth, and the min, well, here the min occurred at 0, so we got to dip it down more. So the min at t equal 1/2 could, for a different function. So that's how to do each of the sides. And they basically are just using Calc 1.
Right. Okay. That is helpful in terms of triangles. What would the process be for something like a disk or an ellipsoid?
Yep. Right now, I think we are dealing with only functions from the plane, R2 to R. If it's ellipsoid, that would be a 3-dimensional case. They are more complicated. Every dimension brings more complication. But let's work on the plane first of all. So here is the overall situation, that we have a function, a real valued function. That means you get real numbers out of it. These are the kind of functions you can maximize and minimize. And you're given a disk and say center at 1, 2, radius 3. And you're asked to find the max and min of f on D. So the maximum minimum of the function on D and D is like this. Part A remains the same. Find the derivative, set it equal to 0, solve. Or this, I guess I call this part 1. To find the critical values, use the Hessian. So it will find all of the critical values on the inside. And then the second part is to find the max and mins on the boundary of D. And this is the part you asked me to focus on.
Mhm.
Are we good?
Yep, yep.
Yep. Okay. So now I'm going to erase this, and this is what we're going to do. In some respects, this is an easier problem than the one we just dealt with. E is a disk in this case. Radius is 3, centered is at 1, 2. So D is this entire thing, and the boundary of D is just this rim right here. There is the boundary. So the boundary of D doesn't have several parts in this case. It is just this single rim. And now you need to parameterize that rim. You need to describe that rim mathematically in order to go further. And there are two standard ways of doing this one. We have an X and a Y axis here. So I could use those X and Y axes. And because I know that the equation here is x minus 1 squared plus y minus 2 squared equals 9. So that's the equation. Mathematica works with functions. So we could solve this for y. So y minus 2 squared is 9 minus the quantity, x minus 1 squared. But now there's a little issue here because y minus 2 is equal to plus or minus the square root of 9 minus x minus 1 squared. So y is either equal to 2 plus the square root of 9 minus x minus 1 squared, or y is equal to 2 minus the square root of 9 minus x minus 1 squared.
Mhm.
Okay, now the first one I will put in red, the red y. The red y parameterizes the top half of this. So these are the points x and then 2 plus the square root of 9 minus x minus 1 squared. And x will go, now we have to figure out the extent of x, because these functions come with domains. And in this case, since we begin here and the radius is 3, the smallest that we could get is minus 2. x value of 1 minus 2 gives me this point. Minus 3 gives me minus 2. So this is actually the point minus 2 here. So minus 2 less than or equal to x less than or equal to, and the largest x can be is 5. 4. The largest x can be is 4. From 1, you can go 3 units to the right. So this is a parameterization for the top. And this is like our U1 in the last example. U1 of x would be this. Continuing this Christmas theme, the bottom half is almost the same. But for the bottom, U2 of x will be equal to x, and then the y value will be this other y value, 2 minus the square root of 9 minus x minus 1 squared. And again, minus 2 less than or equal to x less than or equal to 4. So we have two parameterizations, a top half and a bottom half, and then you need to do each one separately. You do each one separately exactly like we did the last one. I usually change the x value to t. This is called the graph parameterization. I've actually used the graphs here. So I usually use that parameterization, and I use a t, but other than just changing the name of x here to t, this works exactly like the last one.
Okay.
Does this make sense?
That's the part where I was getting a little bit confused on. And then just to get the idea a little bit better though. So both the top half and the bottom half are on the same circle, but they might give different maxima or minima.
Sure. Let's use the same function we had before. F of x and y equals x squared plus y cubed, or minus y cubed x plus 4. I think that was it. So we have, can I erase some of this picture here?
Yep, go ahead, sir.
Okay, so I will erase this and record some data and then go ahead and do some computations. So U1 of, I'll call it T, will be this top one, T2 plus the square root of 9 minus T minus 1 squared, minus 2 less than or equal to T less than or equal to 4. And U2, the bottom of T, is equal to T2, and then 2 minus the square root of 9 minus T minus 1 squared. And again, 0 minus 1 less than or equal to T less than or equal to 4. Okay. So we have to do the same thing for either one. And we'll begin with U1. And U1 is just a start for the top half, the top semicircle. We'll use the function U1 that describes that semicircle. And what we want to do is find the max min for f on U1 of t. So we want to compute this function, f of U1 of t. And f of U1 of t is, well, the x value is just t, so that's easy. T squared minus something cubed, t plus 4. And the y value is this 2 plus the square root of 9 minus t minus 1 squared. So that is what this is. And now I'm going to begin by plotting that function. This is not f. This is plot f1, f of u1 of t, and for -2 less than or equal to t less than or equal to 4. So this should look exactly like we did before. The only difference is that the x and the y are different because we're on a different curve.
Okay.
Okay, so I'm going to do that on my sheet. You could practice on yours if you want. I think I lost my Mathematica somehow, Michael. Oh, I did have it there. Two plus 9 minus. All right. So now I'm going to share screen again. So this is a little more interesting. Here we get a curve that, maybe the very top, so the x is t, so I plug that in. The y is 2 plus the square root here, cubed, times t plus 4. So this is the same process that we did before, only the thing that I plugged in for x's and y's were different. Is this okay? We are good with this?
Yes.
And then now you can actually see probably where the minimum occurs. It occurs somewhere a little bigger than maybe about 2.5 or something like this. The maximum to me looks like it occurs at -1. To actually figure those out, I might use maximize and minimize, n maximize and n minimize for this function on that interval. Maximize and minimize will work well that way too. Or you can just simply take the derivative and set it equal to 0 and solve. All of that you can do with Mathematica. If you take the derivative, set it equal to 0 and solve, and don't use n solve, but use solve, it finds exact values. So this is a way of using Mathematica to find exact values. But at any point here, you should get the idea of where it is. You can see it should be about 2.5 is where the min should occur, maybe 2 1/3, I don't know. And the max does look like it occurs at -1. And then that gives you kind of a check I usually plot these to give myself a check on using maximize or minimize. By the way, maximize and minimize also find exact values. They're supposed to anyway.
Right.
Now,
Okay.
to do
I get how to do that.
let's do one other thing here. Let's do U2. U2 has only one small difference. This is the bottom where the sign,
Mhm.
it becomes a minus. So we could just make that small change. And now let's see what that plot looks like. Aha, quite different. So
Right.
now the maximum is going to occur at 3. And the minimum looks like it occurs at maybe, I don't know, minus a third or minus a fourth,
0.2.
minus 0.2.
Right.
Yeah, something like that. So now that only gives you the maximum and minimum t values. To find the ordered pairs where your maximum and minimum lie, you need to plug into the parameterization that you have.
And then the follow-up to this would be if it's an ellipsoid, so different x and y radii, all that would change is when we're originally fixing the Cartesian equation.
Yes, that's right. That would be an ellipse.
Okay.
Not an ellipsoid refers to a 3-dimensional object.
Sorry.
But
Right, an ellipse.
yeah, with an ellipse, nothing much changes. Let me show you one other thing here, though, Michael.
Mhm.
So if we're good with this idea, I'll just erase this. And there are other ways to describe that boundary that we have other than the one I did. So again, the boundary is just this circle. Its center is at 1, 2, and its radius is 3. You can do the whole thing together with just one function. And we could have used 3 sine or cosine of t minus 1, comma, 3 sine of t minus 2. 0 less than or equal to t less than or equal to 2 pi. So this is the parametric equation for a circle of radius 3 centered at the point 1, 2. So in a way, this saves you some work. You're using trig functions, but you can do the boundary in one. You don't have to do top and bottom separately.
Okay.
If it was an ellipse, like you mentioned before, it had different radius. If the x radius was 5 and the y radius was 2, then that would be it. So it again is just exactly like you said, that you just get small changes in the formulas.
The general form of that formula there, the ut, is radius of x cosine of t minus what number would go there?
This number,
The x naught.
x naught, yeah. So if this is x naught, y naught,
Mhm.
then this is x naught. You're simply taking advantage of the fact that sine squared plus cosine squared is equal to 1.
Right.
And this is the y naught over here. And for a circle, this is the radius, r. And for an ellipse, the first one is the x radius and the second one is the y radius.
Okay, that's perfect.
Ah, you have dogs, Michael.
I have 4 of them, if you can hear them now.
What kind are they?
Each one's a different breed. So there's a Chow Chow, there's a Belgian Malinois, there's a Boston Terrier, and there's a mix between the Boston Terrier and the Chow Chow.
Oh, so that's what was going on.
Right. Yeah. They're lovely, but it goes from tiny little Boston Terrier to a huge Malinois, so
Yeah.
they like to play around. Um, I I think that clarifies all of my questions. There's just one more about the region for squares when coding that, and I would like to share my screen for this one.
Sure. Let me see if I can find this. All right.
Awesome. Um, Perfect. So there was this formula. It gives the general the domain of the square that I'm working on.
Uh-huh.
And when I tried to plot it, rectangle, it was telling me it's not a geometric shape according to Mathematica. But when I looked at the series of them, I found a code called infinite plane. And that did give me an answer. But I'm wondering if that is even giving me the right thing.
I don't think so. But I'm going to look at Mathematica myself for a minute here. And I'm going to look for the command rectangle. Uh-oh. Could try to spell it correctly. So in your Mathematica, look under help. It's in a pull down menu on the top. And yeah, and go under Wolfram documentation and put in the word rectangle. And yeah, so now click on the very first one. Since it begins with an R, that means it's a command. So there it is. And the notation for it is X min, Y min, X max, Y max. So you basically just give it the diagonal. So let's do that in this case.
I have tried this before, rectangle, but for some reason it wasn't accepting it. So rectangle of -1, 3, and -1, 5.
Yeah, let's do this. Let's add right at the end of yours, you have a comma, X, comma, Y. Eliminate that because, okay, now let's try it. Oh, I can't see what it said there.
Let me see if I can load it up. Unfortunately, I can't increase that size.
So I'm gonna try something. I'll just use mine. That should work.
Essentially what it says is that it's unable to resolve the domain where it doesn't recognize rectangle as a membership condition.
Uh-huh. So what was the first coordinate of your first rectangle bracket, and then what was the first point?
-1, 3.
And the second point?
-1, 5.
Oh, no, that's a problem. It's got to be the, let me go see that, where the actual problem was. No, not there, the actual problem that we assigned. Where does it say rectangle? Oh, -1, 3, -1. Oh, I see these. Wait, this is a problem. This should have been, this is my error. This should have been, it should have been 1 to 5, not -1 to 5. Because since the X values are the same, so it should have started at -1, 3 and gone to 1, 5. Try that in your.
Let me just take out an extra bracket. So it's not giving me the error signal anymore, but it's giving me a blank set of brackets now.
Says you can't find the solution. Oh, that means that there is no, that means there is no solution in there. So there is no
Okay,
point in
so
there
it's
where
not
the
wrong.
derivative is 0.
Okay. In which case that means that there's no maxima in the function, and I'd have to go and check the boundaries. Okay, which I can do.
Oh, wait a second here. Let me see the problem again.
Mhm.
Okay, -1, 3, 1, 5, and where they occur. Yes, so let's just take a look at that. We can work on this by hand, Michael, if you have a minute or two.
Yep.
Why don't you read me off the function here?
So f of x and y is equal to 10x squared, y squared, minus 5x squared, minus 4y squared, minus x to the 4th, minus 2y to the 4th.
Looks like 0, 0 should be 1. So if we find the derivative here,
Could you lower the screen a little bit?
yeah. So you could use
Perfect.
Mathematica to find these two, but the derivative with respect to x is 20xy squared minus 10x minus 4x cubed. And then with respect to y is 20x squared y minus 8y minus 8y cubed. And we want when both of these are equal to 0. So we're going to set this equal to 0, 0 and solve. So the first one is 20xy squared minus 10x minus 4x cubed equal to 0. Let's do that one first. We can factor an x out of that. And I get x times 20y squared minus 10 minus 4x squared equal to 0. So either x equals 0 or the second one is 0. So continuing that discussion a little bit, x equals 0 or 20y squared minus 4x squared equals 10. This is actually a hyperbola. We can divide by 2. So we get 10y squared minus 2x squared equals 5.
Mm-hmm.
Now doing the second one, it will be similar, I imagine. So in this case, we get 20 x squared y minus 8y minus 8y cubed equals 0. Factoring out a y, we get y times 20x squared. I guess maybe 4y we can do. So we get 5x squared minus 2y minus 2y cubed equals 0. Oh, minus 2 minus 2y squared equals 0. So again, we get something similar. Either y equals 0 or 5x squared minus 2y squared equals 2. All right, so there's plenty of possibilities here. If x is 0 and y is 0, that's going to be one critical point. 0, 0 is a critical point. And 0, 0 is not in our region, I don't believe.
No.
And then
minus 1, 3, and 1, 5.
Yeah, then x could be 0, but then this second one would be 0. So if x is 0 and 5x squared minus 2y squared equals 2, if x is 0, that would say minus 2y squared equals 2, or y squared equals minus 1, no solution. So putting this with this gives no solution. And now we have to do the other way. Suppose this is 0 and y is 0. Then we're also going to get no solution, because if y is 0, then we get minus 2x squared equals 5. And so x squared would be a negative number. And then the last one is these two. Let's see if we get something there. So here we would get 10y squared equals 5 minus x 5 plus 2x squared. So dividing both sides by 5. By 5. No, let's just solve for y squared. Y squared is 1/2 plus x squared over 5, dividing both sides by 10. So that's from this first one, and then plugging this into the second one tells me that 5x squared minus 2 times y squared, which is 1/2 plus x squared over 5 equals 0. So 5x squared minus 1 minus 2x squared over 5 equals 0. So this is going to give us some additional critical values. We can find these by hand, but Mathematica should be able to find those critical values for us. Let's take out in that last in that last one that you have, let's take out the in the rectangle and let's just have it solve it for x and y and see what we get. I think you've derivative equals 0. I think we've got one extra set of curly braces in there.
I think it might have just been wrong function. Never mind.
Yeah, the one before the dir needs to
I
be
think it
taken out.
fits it.
The one before the dir needs to be taken out, I think.
There we
you
go.
There you go. So it is working. And now let's put back in that rectangle part that you took out. So just XY in that rectangle. Yep. And now we've got to adjust all the crap. I think that's it. Let's try that. Yeah. So it's working for you, Michael.
Awesome. I just got confused by its absence of a presence. Okay.
It actually had
In
something there. It had, so it didn't give you nothing. It gave you this symbol. And this is the symbol for the empty set or no solution.
Okay, perfect. And I think I've seen that pop up, yeah, elsewhere as well. So I understand that what it means now. Okay, that's perfect. That's all the questions that I had, and
Okay,
so
good.
I'll go and work through these and should be done with these. These were the only things that were holding me back.
Okay, good.
Yeah, integration has gone well, and polar coordinates I worked on a little bit previously, and they went relatively fine. So I think we're still on track to do exam 2 for this Friday, if you would be ready with that, sir.
Okay. So I will put it up. I need to, if it is not up, Michael, you need to rate me some kind of message. You can rate me, message me or email me, but I'll try to get that up. I probably can't do it today. It'll take me a little time to write it. But
Yep.
I'll leave myself a note. Hopefully I'll remember, Michael.
I will probably want to meet sometime on Wednesday. I'll send you a message just to go over any last cracks in my mat, and then we should be on track with our schedule then.
Sounds good.
All right, thank you so much, sir.
Okay, you bet. And
I hope you have a great week.
Yeah, thanks, you too. And I will put the recording of this